If there's one thing that you should take away from the integral test is that it should really be your means of last resort when showing a series is convergent or divergent. The problem is it just takes so much time whenever you have a series, you turn that into your integral, but then you have to integrate this integral from 1 to infinity, you have to rewrite it as a limit. It's just a big old mess, and we want to avoid it whenever possible. So pardon me. So what we want to do then is find shortcuts to help us avoid this. And this is what the P-series test is all about. So what is a P-series? A P-series is a very simple series where we have n equals 1 to infinity. Although for convergence, this could actually be any number as long as you don't get a 0 in your denominator there. This is a P-series. A is just some constant positive number into the P. And P is just some real number, and it's going to depend on whether it's bigger than 1 or less than 1, whether this thing converges or diverges. So let's use the integral test on this very general P series. All right. So what are we going to do? We're going to take we'll do this once, and then we'll be done with it forever for a series of this type. So the integral from 1 to infinity of a over x to the p. And let's see, I could rewrite that. It'd be a little bit easier to rewrite that as ax to the negative p, wouldn't it? 1 to b, and b is going to limit to infinity dx. Okay, so what am I going to do here? I'm going to take that x and I'm going to add 1 to the power, and then I have to divide by the new power. So that gets me a over negative p plus 1 from 1 to b. Limit as b goes to infinity. And then let's see, plug in the top. Limit as b goes to infinity of a over negative p plus 1, b to the negative p plus 1, minus, plug in the bottom, a over negative p plus 1, 1 to the negative p plus 1. But hey, 1 raised to any power is 1, so that just goes away. Anyway, it doesn't really matter because this is some finite number. Who really cares, right? What matters is, what's this limit, this gross looking thing here? I can make my life maybe a little bit easier by bringing out this constant multiple of a. I can make that 1 minus p. Maybe that looks a little bit nicer. I don't know. But really it's boiling down to b to the negative p plus 1. What is that limit? And the fact is, this limit depends on the value of p, right? P is not a variable here, it's just an unknown constant. And we're going out to infinity. So obviously, if this whole exponent, in fact, let's just focus on the whole exponent, all right? Maybe that's even easier. All right, there's two cases here. If this whole exponent is bigger than 0, if negative p plus 1 is bigger than 0, then we have infinity raised to a positive power. It's going to diverge. But if negative p plus 1 is less than 0, we have a negative exponent, so we're really dividing by infinity, and that's going to converge to 0. Not that it matters what it converges to, it would converge to 0. All right, but that's a little bit more complicated than we need to write it as. We could just say that this is if p is less than 1, and this is the case where p is bigger than 1. If p is less than 1, it diverges. If p is greater than 1, it converges. What about equal to 1? I didn't really throw that out here right here. Well, that's because I kind of made a mistake earlier. Very sort of technical thing, but if p is equal to 1, actually equal to 1, what is this? Going back up here, if p is equal to 1, then I'm taking the limit as b goes to infinity. That's a over x dx. That's the natural log. That's a whole different case. B goes to infinity, the natural log of a over b minus the natural log of a over 1. Okay, well, what is this going to limit to? Well, if b is going to infinity, then a over b is going to 0, and the natural log of 0 doesn't exist. It limits to negative infinity. This will also diverge. So it diverges for p is equal to 1. All right, so it's this proof's all over the place, but if p is less than 1, it diverges. If it's greater than 1, it converges. But if it's equal to 1, it diverges. So let's go back up here, and here is the p-series test. All right, using everything that happened below this line, here's what the p-series test says. All right, it does one of two things. It converges if p is greater than 1, right? That's what we said down here. But if it's less than 1 or equal to 1, then it diverges. Less than or equal to 1. All right, so there's our p-series test. So when we see p-series, we can immediately, without even thinking almost, tell whether it converges or diverges because it's either going to be a power bigger than 1 or it's going to be a power 1 or less. Okay, so let's take a look at an example. What about this guy? Does it converge or does it diverge? Well, let me just rewrite it as a p-series. And again, the fact that it starts with 2, who cares, right? It's just a finite number of stuff at the beginning that's changing. I could make it 1. It would not change convergence at all. It would change the value if it converged, but not the actual property of convergence. This is m to the 4, but the 10th root. That's 4 over 10. We could write that as 2/5. But what's important is that there's my p, and it's less than 1. It's less than or equal to 1, I should say. All right, so this diverges by the p-series test. Oh man, that was easy. So much easier than actually proving it, right? As soon as we can have this proof that the p-series test works, and we do now, we can just look at the p, look at the power p, and just check if it's less than or equal to 1 or bigger than 1. Okay, let's do one more. Does this guy converge or does it diverge? Okay, well, I don't really recognize this as a p-series, and I don't think there's any way I can get it to look exactly like a p-series, except maybe I could do some reindexing. Okay, what is this bottom here? That's just 1 over, that's j plus 1 squared, right? And I want to make this look like a p-series. I'll just subtract 1 from the j here. All right, but if I subtract 1 from j, I've got to add 1 to the starting j. Okay, and then that cancels, and that gets me the series from j equals 1 to infinity of 1 over j squared. All right, and what is that? That is exactly a p-series. There's the p right there, and it's bigger than 1, strictly bigger than 1. That will tell us that by the p-series test, it converges. Who knows what it converges to? But it converges to some number. All right, and that's all we have to do. We don't have to actually bother to do the integration ourselves. Okay, what else can I say about this? I just want to point out one last note. For p equals 1, what is the p-series? A over n to the p, n equals whatever to infinity. That's just, I can bring out that a as a coefficient, n equals 1 to infinity. 1 over n, this is that very special series called the Harmonic Series. And we should know that the Harmonic Series diverges. It's probably the most famous example of a divergent series. It diverges, but that matches because the p-series test says that if p is greater than or equal to 1, then it should diverge anyway. So that's just another way of thinking of the p equals 1 case. This allows us to take care of so many more types of fractions. However, the other thing I'll mention real quick is that this method of reindexing here is nice and it works, but it's kind of a pain. We're going to learn some more ways to basically say that, well, basically, look, that stuff's not going to matter. We can compare this to the series 1 over j squared if we like. In order to do that, we'll use a thing called a comparison test, a direct comparison or a limit comparison. And that'll give us other ways to show the convergence of this series that are a little bit more straightforward than what I did just now.